Hello everyone. In this video, we're going to start to talk about Lesson 8, which is hypothesis testing for P. Okay. In Lesson 7, we did talk about hypothesis testing at the very beginning, just to say what it is. We give a sentence, okay? So not very in-depth. Lesson 8 is where we go in-depth into what a hypothesis test is, and specifically, if I want to test for a proportion, we talk about the hypothesis test for proportions here. So I want to start with a motivating example that gets us thinking about the types of questions that we want to answer and how a hypothesis test goes in sort of the real world. So I want you to suppose that I give you a coin, okay, and that coin is pretty bent, okay, so it's not a sort of straight coin that we think of. I bent it, but I tell you that the coin is still fair, okay, the coin is still fair, but you don't believe me, okay, which is reasonable if the coin is awfully bent, okay, and so you want to test or give me some conclusive evidence about why the coin is not fair. So we want to test for fairness, okay? So the first question I want to ask you, and I want you to think about a little bit, is how do I begin to go about testing that claim, okay? So it's not enough to look at the coin and say, since the coin is bent, it's not fair, okay? Because it may be possible that the coin is still fair even though it's bent. So that's not good enough, okay? That kind of evidence isn't good enough. Think about how another way where you could test that, and maybe to help your thought, you can think about what kind of tools do we have in this class that can help us, right? That's probably a harder question to answer. I'll give you a second. Okay, so hopefully you stopped your video and thought about how we would go to test that claim. My initial thought is that I can flip the coin a large number of times, okay? Flip the coin a large number of times, and if the result is sufficiently weird, then the coin is unfair. Now, I used some interesting language here that goes along with hypothesis testing. So I know it seems odd, but it's there for a reason, okay? I flip the coin a large number of times, and if the outcome is sufficiently weird, then the result is that the coin is unfair. So what do I mean here? Well, if I flip the coin a bunch of times, let's say 1,000, okay? If I flip the coin 1,000 times, I'm looking at, so the outcome that I'm looking at, or the result that I talk about here, is the number of heads that I see, all right? And sufficiently weird corresponds to how many heads that I see. Some results are going to be not weird if the coin is fair. Okay, so if I tell you the coin is fair and you believe me, there are going to be outcomes that you expect to see, okay, if I flip the coin 1,000 times. For instance, if I flip the coin 1,000 times and 500 heads came up, you would probably not be surprised. Okay? In fact, that's what you should expect, or there's a term in statistics called expected value. Okay? The expected value, if I flip a coin 1,000 times, is 500. Now, that doesn't mean that every time that I flip the coin, I'm going to get 500 heads and 500 tails if the coin is fair. Okay? There's variation there that we learned about in the sampling distributions chapter. Okay? But there are results that are also weird if the coin is fair. For instance, if I flip the coin 1,000 times and the result was 800 heads and 200 tails, that's probably pretty weird, right? That's not what you expect if the coin is fair. And so then you have some doubt about the coin. The real question here is, what is sufficient? So what does sufficiently weird mean? You know, is it, at what point do you start to doubt? So clearly 500 is the most likely, okay? but would you start doubting if the coin is fair if I flipped the 1,000 times and got 560 heads? Okay, or 600, or 700, or 800, and clearly the other way as well. What if I only rolled 450 heads? Or, sorry, flipped 450 heads, or 400, 300, 200, 100. Okay, and so there is a point at which you start to not believe that the coin is fair. We've got to find that point. So, what we need to do is translate that type of thought into the statistical terminology that we're using. So the first thing that we need to do is to understand how a fair coin behaves. Okay? And I've probably used that terminology before. A fair coin is going to behave like this. Okay? So we use a sampling distribution to describe how that coin behaves. And specifically, we're going to use the sampling distribution for proportions, or the sample proportion, the sampling distribution for p hat in this problem. Okay? Instead of looking at the number of heads that we got, we're going to look at the proportion of heads. Okay? So we're just going to divide the number that we got by the total number of flips, and then it becomes a proportion, and then we can use the sampling distribution for p hat. Okay? So a fair coin behaves like this histogram. Okay? So you'll see that it's centered. Its mean is 0.5, which hopefully makes sense, right? Again, if I flip the coin a bunch of times and the proportion of heads is 0.5, then that's fair. But as I get farther and farther away from the proportion, from 0.5, which is my expected number, then the histogram becomes, the height of the bars of the histogram becomes smaller and smaller and smaller, which means it becomes less and less likely that I see one of these numbers out here. Okay, so if the proportion was 0.45 or 0.55, it looks like that's not very likely given that the coin is fair. Okay, given that the coin is fair. So suppose I flip the coin a number of times, a bunch of them, 1,000, 10,000, right? And my result is right there. Okay, so I put an X there and a bar to give you some visual idea of where this is at. Okay, so I flip the coin a bunch of times, and it looks like out of maybe 10,000 flips, 53% of them were heads. Is that enough evidence, so to speak, that I now believe the coin is not fair anymore? Okay, so is that weird enough? That's what we're going to try to find out. Okay, and so how we find out that's weird enough, or how do we gauge that weirdness, is how we've been doing it the whole time with probability. Okay, so we're going to use probability to assess the weirdness. So the questions that I'm going to ask is something like, how likely is it that I actually observed my sample given what we previously believed about the coin? Okay, so we previously believed, or we assumed that the coin was fair, and then we saw that our outcome was really weird and really unlikely if the coin was fair. Okay, we'll use probability to try to assess the weirdness. Hopefully that made sense. If not, we'll have many more opportunities to try to make sense of it. So, this is sort of a formal definition of a hypothesis test, okay? Or we're now talking more concretely about hypothesis tests and not just a question that I'm asking you. A hypothesis test is a test of two competing hypotheses, right? One that was previously believed or known to be true, and one that you believe to be true. So in my example with a coin, the two competing hypotheses were that the coin is fair and that the coin is unfair. Okay. So the first one, the one previously believed or known to be true, or maybe you could think of it as the one that you want to prove is wrong, okay, would be that the coin was fair. Okay, that would be the first hypothesis. And the second one would be the one that you believe to be true, that the coin is unfair. All right? And so hypothesis testing is really going to be like a trial in a court of law. Okay? And so what I mean by that is like the court system. The defendant is innocent until proven guilty. Okay? So the first hypothesis is going to be assumed true unless we can find evidence against it. Okay, so what we like to believe, whether you believe it or not, that you're innocent until proven guilty is what this court system is supposed to be like. Okay, we won't get into issues of that nature here. Okay, but we're going to believe that the first hypothesis is true until proven guilty. All right. You are sort of the prosecutor in this situation, and you're trying to prove guilt. And what you do is you assume innocence, and then prove that it's unlikely based on some evidence. Okay, and the evidence that you are basing it on is the sample that you take. Okay, so what you'll say is, all right, I'll assume that hypothesis is true, and then I'll look at my sample and say that there's no way that this came from that first hypothesis. Okay, so if I flip the coin 1,000 times and say, okay, I'll assume that coin is fair, I'll flip it 1,000 times, and then if I get 800 heads and 200 tails, then I'm going to say, well, that's more than enough evidence that it's like, it's completely unlikely that I get 800 heads if the coin is fair. Okay, and so then you have evidence to the contrary of that first hypothesis. All right, and then when you come to your final decision, your final decision is either guilty or not guilty. Okay, it's not guilty or innocent, it's guilty or not guilty. Okay? The sample either provides evidence to reject that first claim, or it doesn't find enough evidence to suggest the first claim. All right? That last one may seem pretty opaque right now, but when we actually get to the final decision of a hypothesis test, it should make some more sense. Okay? So a quick example, and then we'll finish this video and come back to more in the next one. If we go back to our coin tossing example, my original hypothesis, and I'm going to call that the null hypothesis. Right? My original hypothesis is that the coin is fair. My second hypothesis, which I'm going to call the alternative hypothesis, is that the coin is not fair. So, suppose that I flip the coin 100 times and I observe 65 heads. Is that weird enough to support my claim that the coin is not fair? In other words, does it support my alternative hypothesis, or is it not enough evidence to conclude that the alternative hypothesis is feasible? Okay, do I have to sort of believe the first one or the second one? So what I need to do is I need to understand how a fair coin behaves. Okay, how does a fair coin behave? And so we saw that in a few slides ago. A fair coin, or rather the proportion of heads of a fair coin, behaves according to a normal distribution with a mean of 0.5 and a standard deviation of 0.05. I got those numbers by using the formulas that we used in chapter 6. Okay, sorry, not chapter 6, lesson 6. I assumed, and everything was done, those calculations were done, assuming that the coin was fair, okay? Assuming that P equals 0.5. So it has a normal distribution, mean of 0.5, standard deviation of 0.05. And so the question I'm asking is how likely that I see a sample proportion of 0.65, and then I'll even add on something else, 0.65 or farther away from fairness, given that the coin is really fair. Okay. And so when I do that calculation, okay, and that the calculation, if you want to think in terms of StatCrunch, I'm finding the probability that p hat is greater than 0.65. Okay. And it turns out that actually it could be greater than 0.65 or something weird in the like small p direction. But don't really think about that for now. We'll get back to that. It turns out that there's only a 0.3% chance that that happens. Okay, so there's only a 0.3% chance that I actually see a sample proportion of 0.65, i.e. 65 heads out of 100 flips, if the coin is really fair. All right? And so the final question is, I know I'm asking a lot of questions, and I'm sorry, is that enough evidence to reject that the coin is fair? I would say yes. 0.3% is a very, very small number. Okay, it's very unlikely to see 0.65 if the coin is fair. So, in my mind, yes. Okay, and hopefully in your mind too. Okay, so we're going to end the video here, and we'll come back the next time and talk about concrete steps of how to do a hypothesis test.